Today, we're going to crack open a brilliant algorithm that, and I mean this, is quite literally running the modern world. It was dreamed up way back in 1959, but it's the invisible brain behind your GPS, your internet, and so much more. Let's get into it.
You know, it all boils down to a super simple question. What's the best way to get from point A to point D? But the answer to that really depends on what you mean by best. Because, as you're about to see, the shortest path isn't always what you think it is. For instance, is the shortest path the one with the fewest stops, what we call hops? Or is it the one that covers the least actual distance, in kilometers? Or, and this is where it gets really powerful, maybe the shortest path is actually the one with the lowest cost, which could be time or money or even network lag. The absolute genius of the algorithm we're looking at is that it can figure out the best path for any of those definitions.
So here's our game plan. First, we'll nail down exactly what problem we're solving. Then, we're going to build the map our algorithm is going to read. After that, we'll get into its golden rules, walk through an example step by step, and finally, we'll pull back the curtain on the beautiful, simple reason why it's guaranteed to work every single time.
Okay, so before we can find any path, we obviously need a map. And every map has its own language. In the world of networks, that language is built on just three really simple core ideas.
First up, we've got nodes. Just think of these as your destinations or intersections on the map. They're the points we want to travel between. Could be cities, could be airports, or in the case of the internet, they're the individual routers that shuttle your data around.
Next, we have edges. Super simple. These are just the lines connecting our nodes. An edge is the road between two cities, or it's the fiber optic cable between two routers. It's the path you could take.
But here's the secret sauce. This is what brings the whole map to life. Every edge has a weight. It's just a number that represents the cost of traveling along that edge. This is what turns a simple drawing into a really interesting puzzle. A high weight could mean a really long road or a super slow internet connection. A low weight means it's the path of least resistance.
All right, our map is built. Now let's meet the navigator. Dijkstra's algorithm runs on just a few simple but incredibly powerful rules. This is basically how it thinks its way to the perfect solution.
So, the way this thing works is by giving each node two different kinds of labels for its distance from the start. At first, every path is tentative. It's like a sticky note saying, this is the best route we found so far. But once the algorithm is 100% certain it has found the absolute shortest path to a node, that label becomes permanent. It's locked in. Once it's permanent, the algorithm never has to look at that node again. It's done.
And here's the core loop, the process it follows. First, we start at our source, and we say the distance to itself is 0. Everything else? Infinitely far away for now. Then the loop begins. It finds the closest node with a tentative label, locks in that distance as permanent. And then, from that new spot, it checks on all of its neighbors to see if it just created any new shortcuts. And then it just repeats that simple process over and over, getting smarter with each step.
Okay, enough with the theory, right? Let's get our hands dirty and actually see this thing in action. We're going to solve the puzzle of getting from node A to node D on this map, step by step, just like the algorithm would.
Okay, here we go. We're starting at point A. The distance to get to yourself is always 0, so that's our very first permanent label. Easy. Now, from A, we can only see its immediate neighbors. That's B, which has a cost of 2, and G, which has a cost of 6. We'll jot those down as our first tentative paths.
And now for the first big decision. The algorithm scans every single tentative label on the entire map. Right now, that's just B at 2 and G at 6, and it asks one simple question. Which one is the absolute closest? Well, it's B, with a cost of 2. So we lock in that path. The shortest path to B is now permanent, and B becomes our new base of operations.
So, from our new home base at B, we look out at its neighbors. And hey, this reveals a new path to node E with a total cost of 4. Right? That's the 2 it took to get to B, plus 2 more to get from B to E. So the algorithm scans all its options again. We've got G at a cost of 6, and this new path to E at a cost of 4. The smallest one wins. That's E. So E's path becomes permanent.
And now that E is locked in, it's like we've just unlocked a whole new part of the map. From E, we can now see a path to node C. The total cost is 9, so we'll add that as a new tentative option. We can also see a path to F with a total cost of 11. See how this works? With every permanent node we lock in, our map of what's possible gets clearer and clearer.
So the next few steps just follow that exact same logic. The algorithm would scan the tentative nodes still on the board,
G at 6, C at 9, and F at 11, and it would pick the smallest one, which is G. After exploring from G, the next smallest is C, which becomes permanent, and bam, that finally reveals a path to our destination, D, with the total cost of 14. After F gets its turn, the very last tentative node is D itself. The algorithm makes it permanent, and the puzzle is solved.
So, we found a path. That's great. But, and this is the really big question, how do we know for sure that it's the absolute shortest path? The answer to that is the real magic here. This is the aha moment.
I mean, really think about it for a second. What if there's some secret, sneaky path that winds all over the map that the algorithm just missed? How can we be so totally confident that our path with a cost of 14 is the undisputed champion?
Okay, stick with me, because this is the beautiful part. Let's just pretend for a second there was a secret, shorter path to get to node E. For that to be true, the node right before E on that secret path, we'll call it Z. It has to be closer to the start than E is. But here's the thing. The algorithm has one single, unbreakable rule. It always picks the node with the smallest label to make permanent next. So if Z was actually closer, the algorithm would have found it and made its path permanent before it ever even considered E. By the time the algorithm chooses to make E permanent, it has already proven that no shorter way to get there could possibly exist. It's just logically impossible.
And the craziest part of all of this perfect, elegant solution wasn't invented last year by some AI. It was conceived by a Dutch computer scientist named Edgar Dijkstra all the way back in 1959. It's a foundational piece of computer science that has absolutely stood the test of time.
And this is not just some abstract puzzle. By just changing what that weight number represents, this exact same logic is used to find the path with the least delay for your internet traffic, the most efficient route for a delivery truck, or even how a character in a video game finds its way across a complex map. It's everywhere.
You know, it's just an amazing reminder that sometimes the most complicated problems have these beautifully simple, elegant solutions. Which makes you wonder, now that we've mastered finding the shortest path, what's the next great puzzle technology is going to solve for us? Thanks for digging into this with me.